Hi everyone. So today we're going to look at some data about driving safety. So we're going to be looking at reaction time and stopping distance and how far you're going to go once you step on those brakes. And you're going to see that you really shouldn't be that close to people if you think about it in terms of how far away you should be the minute you step on your brakes and how much of your reaction time you have. All right, so let's talk about this reaction time. The time that the average alert driver takes from switching from the gas pedal to the brake, usually about 0.75 seconds to 1.5 seconds. This is really important. We're going to be using that during the course of the video. But again, keywords here are alert driver. Think about what happens to that reaction time if you're not alert. Reaction distance is the distance a car travels during reaction or thinking time while drivers switch from the gas to the brake. Okay, and your braking distance is the distance a car travels while the braking is to complete stop. And then you have total stopping distance, which is the sum of the reaction distance and the braking distance. So this is going to tell you how far you're going to completely go between your reaction distance and your braking distance. So we're going to be adding these two together and they're going to equal your total stopping distance. So here's some facts that we're going to be using during the course. So keep in mind there are 5,280 feet in a mile, and on average a car traveling 55 miles per hour covers 55 miles in 1 hour. A car traveling at 55 miles an hour covers 290,400 feet in 1 hour, and 55 miles covers 4,840 feet in 1 minute, or 80.67 feet in 1 second. All right, so what is the reaction time, or reaction distance, for a car traveling approximately 48 miles per hour? Well, we don't have any data on 48, like it's not any in our facts here. So let's just talk about doing 55 and see if we can get like an estimate of where 48 would be. Okay, so since we're talking about reaction time of approximately 48 miles per hour, let's do it in feet per second, okay? All right, so let's make that 81. It's going to make life so much easier. So it travels 81 feet in 1 second. And our reaction distance is 0.75 to 1.5 seconds. So we want to know how far he's going to travel in 0.75 seconds. Okay, so we're going to do two of these, one for the 0.75 and one for the 1.5. All right, so we're going to do cross product. I'm sure we're all familiar with that. And so we're going to get about 60.75 feet. All right, so that's at 55 miles per hour. Okay, so let's do the other one. So we're going to go 81 feet in 1 second. And we want to know how far we're going to go in 1.5 seconds because that's our reaction time. Again, we're going to do cross product. Okay, so when we do that cross product, we're going to get 121.5 feet. Now again, this is for 55 miles per hour. So if we're going 48, it's probably going to be a little lower, okay? In fact, research has shown that on average, so this is kind of like a rule of thumb, or shall we say, so let's call this a rule for reaction time. I'm sorry, I keep using time. Reaction distance is that a car travels about, and again, this is just about 1 foot for each mile per hour in speed. Okay, so if that's the case, because again, we're doing like 60 to 125 approximate here, and we're doing 48. So let's say our answer is 48 feet. Okay, so again, this is kind of the general rule of thumb. All right. So let's try this one. A car is traveling 65 miles per hour. Approximately how far will it travel during the average reaction time? And again, this is 65, which is the speed limit on 78, and it's how far your car is going to travel between taking the foot off the gas and putting your foot on the brake. It's going to be 65 feet. Okay? Because it's going to be approximately the same as your miles per hour. All right, so that's how long it's going to take you to take your foot off the gas and step on the brake, how far your car is going to travel. Now, braking distance is from when you put your foot on the brake, how far is your car going to travel until it comes to a complete stop. So we have this formula called the braking distance formula, and it says S squared divided by 20. Now, S is your speed of the car. And currently, we're going to be in miles per hour. Okay. All right, so we're going 48 miles per hour. So we're going to take 48, we're going to square that, and then we're going to divide that by 20. And again, there's a way to derive this formula. So, but I think we're okay with saying, here it is. So 48 squared divided by 20, and I got 115.2 feet. Okay, so that's not real short. Okay, so let's try this one. What approximate braking distance of a car traveling 65 miles per hour? What factors do you think would also take into account that might detract or add to this braking stopping distance? All right, so we're going to go 65. So 65. Let's try that again. 65 squared divided by 20. Okay, and I'm going to get about 276. Oh, no, I'm sorry. That is not right. Press the wrong buttons there. 211.25 feet. Okay, now if you think about it, what other things are going to contribute to your braking distance? Okay, what about road conditions? Is there a difference in your braking distance if the road is wet or if there's snow or ice? Okay. What about your tires? Is there enough tread on there, or are they bald, or are they properly inflated? Okay. What about you yourself? Okay. Are you impaired? And these are just a few things that would contribute to or from your braking distance. All right. So let's talk about Rachel here, and she's driving about 48 miles per hour in a one-lane highway. She sees an accident right ahead of her. Oh boy, about 200 feet. Will she be able to stop? Okay, so total distance. Will she have enough room to stop between the time she takes her foot off the gas, okay, and put her foot on the brake? Now remember, taking her foot off the gas, okay, and putting her foot off the brake is the reaction distance. And we have to take into consideration braking distance. So our total stopping distance is reaction distance plus braking distance. Now, luckily, we already did both of these. Okay, so she's traveling at 48 miles per hour, so her reaction distance is about 48 feet. And her braking distance, which was up here, 115.2 feet. Okay, so when we add the two of them together, we get 163.2 feet. Okay, so it looks like, because remember, we want to know, will she be able to stop before she hits that 200? Yes, so she will be able to stop in time. Okay, so about 37, 36 feet to spare. Okay, so what's the total stopping distance for a car traveling at 65? And again, we did the two parts earlier, so our reaction time is 65 feet. Okay. Plus the 211.25 feet. Okay, so that's 276.25 feet. Okay, now if we were at the same situation and this person was traveling 65 and ran into that same situation 200 feet ahead with the accident, that person would be part of the accident. Okay, so now we have Desiree, who's traveling through Canada, and her speedometer in her rented car indicates kilometers per hour. All of the road signs give distances in kilometers, and she knows that 1 kilometer is about 1,000 meters, and 1 meter is a little bit more than 3 feet. Determining Desiree's total stopping distance in meters if she was traveling at 88 kilometers per hour. Now we can do this two ways. Okay, and we're going to do both. We're going to take her 88 kilometers per hour, we're going to convert it to miles, do our work, and then convert it back to kilometers. And then we're going to go and do another formula where we can keep it just in kilometers. Okay, so we're going to do some conversions first, and then we're going to use a different formula. All right, so let's do it in the conversion. So we're going to convert. Okay. All right, so we remember from the other day that 1 kilometer, okay, is equal to 0.62. Stick a 0 in there. 13712 miles. Okay, so we're going to do some conversions here. So we're going to take her 88 and we're going to times it by the 0.621371 to convert it to miles. Okay, so we get about 54.68 miles per hour. Okay, so that's the conversion. All right, now we're going to take her reaction distance plus her braking distance and see what her total braking distance would, total stopping distance. Okay, so her total stopping, okay, is we're going to take her stopping or reaction, which is going to be 54.68 plus 54.68 squared divided by 20. I always forget. Yep, divided by 20. Okay, so there's our formula. Okay, stopping distance, reaction distance plus, or speed plus speed squared divided by 20. Okay, so I got about 204, let's say 175 feet. Okay, now that is again in feet. So now what we're going to want to do is convert that back to kilometers. Okay, so we're going to take our 2004.175 feet and we're going to times it by the 0.3048. That gets us back to kilometers. 62.23 meters. Okay. All right. And again, that 0.048 was in our notes the other day. Okay, so that's doing the conversion. I'm running out of room, so I'm going to do this down here. So alternatively, there are our other formulas. So let's label this total stopping distance in meters. Okay. All right, so there's a formula, and it's going to be s squared over 170 plus s over 5. And again, I'm sure we can derive this, but kind of just go with it. And remember, s is going to be in meters, okay, or your speed. So this is going to be, if I wanted to leave it in meters, it's going to be 88 kilometers squared over 170 plus 88 over 5. Okay, so when we do the math, okay, so square 88 divided by 170, square 88 divided by 5, add the two together, we're going to get about 63.15 meters. Okay, all right, so we were a little off with our conversion. Again, decimals are going to do that for us. Okay, all right, so let's try this particular one. All right, so a car is traveling 78 kilometers per hour. What is the total stopping distance in meters? I'm going to use the stopping distance in meters. I don't feel like doing the conversions. And there's no reason to once we have this formula. So I'm going to go 78 squared over 170 plus 78 over 5. Okay, so we're going to do the math here. And I got 51.39 meters. All right, last one. Here we have Tony, and he's traveling at 75 kilometers per hour. Then you have Randy, who's behind Tony, and is traveling at 72 kilometers per hour. Tony notices a family of little ducklings crossing the road 50 meters ahead of her. Will she be able to stop before she hits the ducks? First question. And how far back is Randy going to hit Tony if she stops? Okay, so if he reacts the minute he sees her brakes. So let's start with Tony, and the first question is, will she be able to stop before she hits the ducks? So let's find her total stopping distance. Okay, so let's talk about Tony here. All right, Tony total, let's call it that. So we're going to do 75 squared over 170 plus 75 over 5. Okay, all right, so 75 squared divided by 170 plus 75 divided by 5. Okay, so I got 48.09 meters. Okay, so will she hit the ducks? No. Okay, so we're good. Will she be able to stop before she reaches the ducks? Yes, she will be able to stop. Okay, so Tony's happy. She'll be able to stop without hitting the ducks. But she has another problem because Randy's behind her. Will Randy hit her? Okay, so let's look at Randy. So let's talk about Randy's distance. Let's do total for Randy. Okay, so Randy was going 72. Okay, so let's find his total. So 72 squared over 170 plus 72 over 5. And I thought I just had that, but I guess I don't. So here we go. All right, I have 44.89 meters. Okay, all right, so, well, that's good because notice that Randy is smaller than Tony, so there's going to be some space in between. So let's find the difference. Okay, what is the least distance Randy's car can be from Tony's car to avoid hitting the car if he reacts as soon as he sees her brakes? So let's find the difference. Okay, so 48.09 minus 44.89, and we're going to get, I was just checking my math, 3.2 meters. Okay, not a whole lot of meters. That's just about a yard, maybe a little over. All right, so that's pretty close, but he does not hit Tony. All right, guys, let me know if you have any questions. Remember, to stay safe means we're going to stay in and keep each other safe. I'll talk to you again real soon.